Okay, so for this scan approach, people have used this in a lot of medical image applications. So the first one, the example we look at is the low dose CT denoising. Okay, so the input is a low dose CT input. So the low dosage CT means the ionized radiation, the dosage is very small, right? Because we know that the computer tomography, right, using ionized radiation to generate the image, right? So, but this kind of radiation may raise concerns to, for the patients, right? So they don't want to expose to, high dosage of this kind of radiation. So one way to address that is we can using a small amount or low dosage of radiation to generate the CT. But the limitation is that the resolution of the generated image will be low quality, okay? So you may have a lot of noise, the resolution may not be very clear, and this will definitely affect the later diagnosis, right? Because some of the pathology may not able to, or disease may not able to be identified based on the noisy or low quality input. So the goal is that can we using GAN, right, to enhance or denoise the low dose CT image. Okay, so the goal is that given this low dose CT input, we want to generate this denoised high quality CT image, which resemble the conventional CT, right? If you are using the regular dosage of radiation. Okay, so that's their objective. So how do they achieve that? So it's very simple. They also using this conditional GAN approach, right? So you have this input, low dosage CT image, SX. It will go through a generator, G, and will generate a virtual conventional CT, right? The conventional CT means this is a denoised or high quality CT image. And this is called virtual because it is generated by this generator, okay? So this is a synthesized conventional CT image indicated by white hat, right? So for their loss function, they have this usual GAN loss, right? You have the real pair, right? So you can have a real conventional image. And this is the generated image, white hat, and you can feed that into the conditional GAN, have the usual GAN loss. In addition to this usual GAN loss, they also have two additional one that is measure the sharpness of the image. Okay, so they have these two images, right? The original conventional CT and this virtual conventional CT, and they're using some edge detector, right, to detect the edges, and they want to measure how sharp is the generated CT as compared to the ground truth, right? And the reason they care about the sharpness is because for the CT or for some of the diagnosis, some of the edges or contours are very important. So they want to make sure that the generated CT is going to preserve some of the sharpness as compared to the original conventional CT. So that's one additional loss they add to their approach. And the third one, this is, again, this is the similar to the conditional GAN. They also have this L1 loss, right, to make sure the content should be very similar to the conventional CT, right, original input. So to generate this data, right, so here they are using paired data, right? It's not like unpaired image to image translation. So the way they generate the data is they simulate this low dose CT image by adding additional noise, right? So you can take the conventional CT and adding noise to the data, or you can, do some image degradation to generate the corresponding low quality data. Then you have a training pair, right? So you can train this conditional GAN using this training set, okay? And this paper here using this MRI to CT synthesis using CycleGAN, right? So the idea or the methodology, again, adopt this CycleGAN approach, but here the application is we want to generate MRI, generate CT from MRI, right? So as we learned from previous lecture, right? So these different modalities contain different information, right? Oftentimes, if we use multiple modalities like MRI, CT, or X-ray, we are able to leverage all these information to make a more accurate diagnosis. So, but not all these modalities are always available, right? So for some of the hospitals, they may only have CT images from the patient. For some of the cases or scenarios, they may only have MRI images from the patients. So this paper trying to using CycleGAN to synthesize other modalities, right? So that we can using the generated data to perform a more comprehensive or more accurate diagnosis. So this methodology-wise, there's nothing new, I guess. More just using this CycleGAN approach to perform this MRI to CT synthesis. Okay. And this is their result, right? So we have this input of MRI image of the brain, and this is the synthesized CT image, and this is their ground truth of the which has corresponded to this MRI image, right? So visually they look very similar, right? So all these different tissues, structures has been preserved, and on the first glance, right, they are very close to each other. But when they actually compute the difference, right, we can plot or visualize the difference. For some of the regions, you can still see the general image is not perfect. They have some large difference as compared to the ground truth. The next example is we can using GAN to do the segmentation task, right? So here they are doing this organ segmentation in chest X-rays. So the input is the chest X-ray image. Okay, then we are using some segmentation network, right? So we can using a UNet or maybe VNet or 3D UNet, not 3D UNet here because X-ray is a 2D. We can using other, UNet variants, right? Attention UNet, have this encoder decoder structure to generate this segmentation map, right? So this is the predicted mask, okay, or segmentation map of different organs. And for the training data set, we have the ground truth map, right? So this is the ground truth mask. And we can train this discriminator, right, to, or they call it critique network, to tell if this predicted mask is going to be real or fake, okay? Real means this is very close to the ground truth. Fake means you have very different from the ground truth, right? And their generator is going to be the segmentation network. Okay, so they are able to formulate this segmentation into this kind of GAN training framework, right? You have this segmentation network as a generator, and you have additional discriminator to kind of distinguish this predict map as compared, to the ground truth segmentation map. Okay, so if we do this GAN training, ultimately, the classification or this critique network is not going to tell, right, if this is going to be real or fake, right? That means the predict mask is very close to the ground truth, right? And that means the segmentation network or the generator is able to do a very good job generating the segmentation. Okay, so that's their idea. And in this example, they are doing EEG to image generation. So again, this is like two data modalities, right? Before we look at MRI to CT or CT to MRI. Here, they want to, do image, EEG to image translation. Okay, so it's like you can read a person's mind, right? So the EEG is monitoring the brain activity, right? Generate these multi-channel signals, right? Like this. And we can train, we can using the, GAN approach, right? To generate the corresponding image, right? And because the training data is this person is actually looking at a specific image, and you will stimulate different region of the brain and generate this EEG waveform, right? If you look at a different image, this EEG signal will also be changed, right? So actually, we can have like a training data set, right? Which EEG signal corresponding to which data, which image, and we can train this GAN network to train a very good generator, right? And then during the inference stage, right, we don't know what this user is actually looking at, what picture, but based on this EEG signal and with this trained generator network, we are able to predict, right, what image this user is actually looking at. Okay, so that's the idea of doing this kind of EEG-based image generation, this kind of like a brain-computer interface. And this is their network. So we all know how it goes, right? The generator and the discriminator to tell if this is real or fake. But let's look at some of the examples they are able to generate. So here are some of the images they generated by this or predicted by this generator. So this is airliners, right? Different planes. So actually the input EEG is corresponding to this particular class, and this is the image the generator is able to predict. Obviously, these images are not perfect, right? So I think none of them can be considered very realistic to like an airline. But some of the characteristics or attributes are there, right? You have wings, you have some tires, right? So they have background of blue skies or cloud, right? So for a human, we can guess, right? This is an airline, right? Airliner, right? Or plane, right? And here, another example, right? So the input is the EEG signal corresponding to the user looking at this Panda image. And this is the generated image, right? Again, they are not perfect, right? This cannot be considered like a realistic Panda image, but again, some of the key attributes are there, right? You have this the white and the dark black color, and you may have some eyes or ears, right? And even have some vegetations, maybe bamboos, right? Because panda eat bamboos, right? So we can guess, right? This is a panda image. So visually, right? So this give a very educated or very high quality, we can give a very high quality guess, right? What exactly this user is looking at. So so far we've kind of looked at different approaches that we are able to generate a realistic image, right? So they are look very visually pleasing and realistic, and especially some of the faces, right? Facial images have been generated. So basically, you're not able to tell, right, if this is a real person or this is actually a fake person generated by GAN network. So this raised some concerns, right? So so there's this technique or method called deep fake, right? So they are able to generate not realistic image, but actually realistic videos. Okay, so the kind of presenting like the real person is talking or maybe doing some of the activities, right, in the kitchen, or maybe doing some other activities there. So this will raise some concerns, right? Because if this kind of technology getting to the wrong hand, right? So this could be, cause some of the disasters, right? Maybe a person released some of the fake video, right? Maybe from the president doing some fake announcement on news, right? This will cause panic, right? So that's why there's also technique trying to detect if the images or videos are generated by this kind of deep fake technique. So here the Meta actually host this kind of a deep fake challenge, right? So they have this data set. Some of them are real images or videos, and some of them are generated by this generative models. So the challenge is you want to develop some of the algorithm is able to detect those generated images or videos accurately. Okay, so this is just something we have to be mindful, right? So this can also be have a bad impact or bad side of this kind of approach or technique. Okay. Okay, so here are some of the more reference for generative adversarial network for medical image computing. So if you're interested, you can go through these lists and the papers and maybe know more about GAN have been applied in medical domain. Okay, so talk about this generative general model. So recently there is also this diffusion model, right? So gain a lot of hypes or interest in computer vision domain, right? So it will generate high quality images. Some of them are even surpass the images generated by GAN. So those are also very interesting directions actually in the medical image computing domain. So there's also, I think, several or maybe a list of papers using GAN, using the diffusion model now to do image generation and segmentation as well. So that may be also something you guys can look into. Okay.